Hello and welcome to graph analysis. This session is very special. You know that physics is the struggle of humankind to find the reality. In physics, we use math language, and in math, we have a lot of tools. For example, we have formulas, numbers, ratios, relations. Sometimes we use graphs. Graphs are really beautiful. In my opinion, graph is something to visualize the nature or visualize a reality. Sometimes the reality may be really, really complicated, and with the graph, we can make it understandable. Sometimes we make a graph to find a relation for the nature, to find a formula. Sometimes we have a formula and we draw a graph to understand that formula. How to analyze the graph? What the graph really is? Let's learn it. So let me turn off the camera and give you a full concentration on the screen and learn what the graph analysis is. Let's start. Okay, look at this relation. Y is equal to 3x plus 4. It's a linear function. Why? Because x and y are both in the power of 1. Okay, if I visualize that, y versus x may be a line with the positive slope and the positive y-intercept. The y-intercept is 4. So it must intercept the y-axis at the positive point of 4, and then 3 is the slope of that line. You know what the slope is, and so forget about that. First, I had a relation, I had a linear function, and then I drew a graph for that. Sometimes the situation is inverse. You have a graph based on some measurements, you have some points, and then you connect those points and find a line, and then you measure the slope of that line, and then you measure the y-intercept and write a relation for that. Y is equal to 2x plus 3. The situation here is different. First, you have the line, and then you make a relation. You make a function for that. Error bars, zone of uncertainty. This is a coordinate system of y versus x. Y and x could be arbitrary quantities. If they are quantities, I should measure them. If I make a measurement, I may have a value for x like 5 and a value for y like 4. How should I specify that measurement in this coordinate system? It's very easy. I should go 5 steps to the right and 4 steps upwards and then specify that point. But you know this is not a mathematical point to be that exact. Anyway, if they are quantities, they may have a certain degree of uncertainty. So x must have its own uncertainty. Suppose that the uncertainty is plus or minus 1. How should I show that uncertainty? Here I use error bars. Error bars, something like this. I go 1 step to the right and 1 step to the left based on the given 1, and then I show that x must be something between 4 and 6, not exactly 5. I do the same thing for y. Suppose that the uncertainty for y is 1.3. So from here, I should go 1.3 upwards and the same value downwards to make the vertical error bar. These error bars make a zone for me, a rectangular zone, which is named zone of uncertainty. The value, the real value, is something in this rectangle. Not exactly at the center, but everywhere on this area. Possible lines. Suppose that I do measurements and I find 5 points with their own uncertainty zones. Then I try my best to draw a line or a curve passing through all uncertainty zones. It could be one of them, and also it could be the other one and the other one. You see that here y versus x indicates a linear relation because I can draw a line passing through all uncertainty zones, but unfortunately there are a lot of options for me. It's not just one line. What should I do? Among them, one line is named best fit line, which may have linear relation like that, y equals mx plus b. M is the special slope for that best fit line, and b is the y-intercept of that best fit line. How should I find m and b? Let's learn it. Slope of best fit line. These are the given points or measured points with the uncertainties, and I'm gonna find the slope of that. First, the slope. I ask you, please forget about the middle points and just concentrate on the first and the last uncertainty zones. For the last uncertainty zone, concentrate on the top left and the first one bottom right. Then connect them to find the maximum slope among the possible lines. M max is the maximum slope possible for my thousands of options for the lines. M max. Then I do something similar for finding the minimum slope. The last uncertainty zone will have the bottom right corner like this and the first one top left. I connect them to find the minimum slope among my options. Then I find the slope of the best fit line to be maximum slope plus minimum slope over 2. This is the average. And then it might have its uncertainty. So I should write the uncertainty of the slope is going to be m max minus m min over 2. It's half of the range. So I have average for the value and half of the range for the uncertainty. These are the properties of the slope. Still, I have something more to learn, which is the y-intercept. Let's learn it. Okay, now let's concentrate on y-intercept of the best fit line. Here, maximum slope is for the red line and the minimum slope is for the blue line. I extend the red line like this. It has an intercept with y-axis, with vertical axis, and so let's name it b minimum. As you see, the maximum slope gives minimum y-intercept. Also, I can extend the blue line with the minimum slope to find the maximum y-intercept, and let's name it b max. Now, we do the same thing. We have the same strategy for finding the best fit line y-intercept. Here is the b max plus b min over 2, and the uncertainty of that will be b max minus b min over 2, half of the range. So the average will give you the best fit line's vertical y-intercept, and uncertainty for that will be half of the range. Now we are ready to write the equation of that line. Y is equal to mx plus b. If this is the equation for the best fit line, m is something we find it with the average of m max and m min, and b is something we find it with the average of b max and b min, with the uncertainty as mentioned. Proportional versus linear graph. Can I say that the linear relation is always proportionality? No. Let's have a very simple equation like this. Y equals mx, and the y-intercept is going to be 0. The graph of this line will pass through the origin with a slope of m, maybe positive, maybe negative. It's not that important now. I will take a certain value, an arbitrary value for x, and then I put it to the equation, and then I will get the corresponding value for y. It's y1. Then I put another value to this machine, and then it's x2. The corresponding value for y will be y2. Here, you know that y2 over y1 is equal to mx2 over mx1. As I can forget about m, this is easy to write. Y2 over y1 is equal to x2 over x1. This linear relation is also carrying the meaning of proportionality. This is proportional relation rather than the linear graph. Sometimes it is not possible because we have a y-intercept. Suppose that I have y equals mx plus b. There is a y-intercept, so the line won't pass through the origin. if I take the same corresponding values, for example, suppose that I get x1 and y1 and x2 and y2 based on the equation. Here y2 over y1 will be mx2 plus b and mx1 plus b downstairs. Unfortunately, I cannot forget about m. Here, m is something to be regarded because of the b. So here, I cannot write y2 over y1 is equal to x2 over x1. This is something not possible for the case. So the proportional relation is the linear relation with no y-intercept. If there is a y-intercept, we have the linear graph, we have the linear relation, but it is not regarded as a proportional relation. Okay, an example could be the temperature. The Kelvin temperature and the Celsius temperature are related like this. T is equal to theta plus 273. You know, in physics, it's very famous relation. Here, T2 over T1 is not going to be equal to theta 2 over theta 1. Why? Because I have, unfortunately, the vertical intercept. And this is different from a proportional relation. It's just linear one, but not proportional. Means that if you multiply theta by 10, for example, you cannot say that I simultaneously have multiplied t by 10. No, it's not true, because we have 273 as the y-intercept. Be careful about such relation. Here, I have something more for you. Bacterial population versus time. Suppose that in biology, in a different field of science anyway, I have found graph like this. This is based on an experiment. I have 4 uncertainty zones and I try my best to pass a line through all uncertainty zones. Unfortunately, this line will miss the last point, and this line also has the same property. It cannot pass through all the uncertainty zones. And if I select this line, I will miss 2 of them. It's not good. So if I try to pass a line through all uncertainty zones, it will be impossible for me. It's not successful strategy. What should I do here? I should try to have not a linear, but a curvilinear one. It's a kinked graph. It could be a curve. Yeah, it is an accepted graph. This is named the best fit line, but unfortunately it's not a line. But the name is also best fit line. Also, this one is possible because anyway, it's passing through all the uncertainty zones. So I should remind you that the best fit line must pass through all uncertainty zones, and best fit line is not necessarily a line. So when I say best fit line, I do not say necessarily that there is a linear relation. It could be a non-linear one, but the name is still best fit line. Okay, I hope that this lesson till now has been instructive for you. Now this is the time to have some more activities based on the problem solution. Let's solve some problems to learn it more and understand more concepts. Problem 1. In an experiment to measure current and voltage across a device, the following data was collected. V and I, it's given in 4 couple of values. The current was measured in milliamps and the voltage in millivolts. The uncertainty in the current is plus or minus 4 milliamps. Plot the current versus the voltage and draw the best fit line through the points. Suggest whether the current is proportional to the voltage. Look at this part, draw the best fit line. When they say draw the best fit line, it is not necessary to do some calculation. It's enough just to draw the maximum and the minimum slope lines, and the best fit line will lie in between. Okay, let's start. I put the given values here and the uncertainty in current. As I told you, there is nothing given for the uncertainty in voltage. On vertical axis, I take current in milliamps. Here is 50 and then 100 milliamps. The values for the voltage in millivolts are on horizontal axis, 0.1 to 0.5. I think it's a good scale for drawing. Let's start to find the points. I will have 4 points based on the 4 couple of values given. The first will have the voltage of 0.1 here and the current of 26. If here is 25, 26 is a little bit more something here. Yeah, this is the first point. For the second one, 0.2 for the voltage and 48 for the current. 48 is a little bit smaller than 50, so it must be here, yeah. The third point, 0.3 and 65, somewhere like this, and 0.4 and 90, the last point. This is the last point, yeah, the 4 points. Then I need to add the uncertainty zones and first of all, the error bars. I don't have anything for the error bars for the voltage, so I just add an extension for each point vertically, plus 4 milliamps and minus 4 milliamps, something like this, here, 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 and here. This is the vertical extension I add. So the uncertainty zone will include just that vertical segments I have added already. Nothing more. It's not gonna be a kind of rectangle. Okay, let's draw the maximum slope, the minimum slope, and then the best fit line judged by eyes. The maximum slope is found when you connect the bottom point for the first. The bottom part of the first means that you look at the first point and go downwards to the minimum possible value for that and connect it to the maximum for the last one. The last point is here, but the maximum value is a little bit more than 90 because it is 90 milliamps, but as you add 4 milliamps, it will be 94. So I will connect here. It's 26 minus 4, it's 22. 22 is connected to 90. Something like this. This is the maximum possible slope for the given data points. For the minimum slope, you will connect the first to the last, but for the first one, I connect the top, and for the last one, I will take the bottom part. So these 2 points. Then I connect these two. Yeah, this is the minimum slope. Then everything in between could be regarded as the best fit line, but judged by eyes. This green line, green dashed line. But can I say that the current versus voltage indicates a proportionality? No. This is, of course, a line, but this line will not pass through the origin. It has a y-intercept, vertical intercept in this case. So I think current is not proportional to the voltage as the best fit line does not pass through origin. That's all. Problem 2. A student performs an experiment with a paper toy that rotates as it falls slowly through the air. After release, the paper toy quickly attains a constant vertical speed as measured over a fixed vertical distance. This is the paper toy, and it is released from rest. So let's name it point A, and from the point A, it starts coming down with accelerated motion maybe to the point B. So it's accelerated motion. And then it gets a terminal speed, a constant speed, and goes with that speed from B to C. Okay, so from here to here, it is a constant speed motion. The aim of the experiment was to find how terminal speed, this is terminal speed, let's name it V, how terminal speed of the paper toy varies with its weight. So we should increase the weight or decrease the weight. The weight of the paper toy was changed by using different numbers of paper sheets in its construction. Okay, so we named the number of paper sheets n. We increase the n, and then we check the velocity. We check the speed. So speed may change with n. I think we may have a graph like this. Terminal speed versus n, number of paper sheets. Let's check it. Yeah. The graph shows a plot of terminal speed v, this is terminal speed v, in meters per second, of the paper toy calculated from the raw data, and the number of paper sheets, n, used to construct the toy. Okay, here I have number of paper sheets. Number necessarily will be an integer. So it starts from 1, goes to 6, maximum 6 paper sheets. Okay, then the uncertainty in V for n equals 1 is shown by the error bar. Yeah, here I just see the uncertainty for n equals 1. Okay, let's continue. A. The fixed distance is 0.75 meters, 75 centimeters, and has an absolute uncertainty of 0.01 meter, maybe 1 centimeter. So, in other words, I can say the distance is d. Let's show that value here. The distance is d, the fixed distance, 75 centimeters, in other words, and plus or minus 1 centimeter as the uncertainty. Okay, the percentage uncertainty in the time taken to fall through the fixed distance is 5%. So if it takes a time like t, the delta t over t is gonna be 5%. 5%. It's very important. We don't have absolute uncertainty for time, and we don't have time even. We have just delta t over t, 5%. Okay, calculate the absolute uncertainty in the terminal speed of the paper toy for n equals 6. We are going to find the absolute uncertainty, but you may remember that speed and time and distance are related like this. If the fixed distance is going to be x, we can write v is equal to x over t. Okay. Here we are faced with multiplication and division. So for uncertainty, we should go first for fractional uncertainty, then absolute uncertainty. I have already mentioned that in the previous video. So let's start. V equals x over t. So delta v over v will be delta x over x plus delta t over t. Okay, what should I do next? I should substitute the values. Delta t over t is 5%. It's here. Exactly, it's here. So we have that, the last term. About the other values, the velocity v is here. We can easily find it because I'm going to find it just for n equals 6. So it's for n equals 6. So the velocity must be something like this, maybe 0.40. And delta x and x. Okay, delta x is the uncertainty in the distance given here, 1 centimeter, and x is given here, 75 centimeters. We can put delta x over x with delta x and x with the units of centimeter or unit of meter. It's okay, no problem at all. Okay, let's erase all. And then, yeah, the values are here. Delta v over v, I told you why, 0.40, 0.01, 0.75 for x, and this is delta t over t. That's all. You should just do the calculation and find delta v to be 0.025 meters per second. This delta v is the uncertainty for the velocity, but pay attention, this uncertainty belongs to the n equals 6 only. It is not applied for the other values. The uncertainty in each case may be different. Let's continue. Double I. On the graph, draw an error bar on the point corresponding to n equals 6. Okay, we are going to have a visualization for the uncertainty for the velocity. So let's remind you the velocity had the uncertainty of 0.025 meters per second, not for all values, just for n equals 6. I'm going to show that with error bars. You may remember that if I have a point on a graph and the uncertainty to be anything like um, x, like everything, we should go to the same value upwards and then extend it downwards with the same value of the uncertainty, and then it's gonna be my error bar. So as the value is 0.25 here, I go the same value upwards and downwards to make it as an error bar. So look at here, for example, here from 0.35 to 0.40 is exactly the same value as here. As I see here, I have 0.05, which is exactly 0.05, the total length of my error bar. So I think it's a good idea to put the same value here. So I've extended the vertically that point on n equals 6. This is just indicating the uncertainty for the velocity and at point n equals 6, not any other point. On the graph, draw a line of best fit for the data points. I told you line of best fit is not necessarily a line, even it could be a curve. So do not insist on taking a line here, because if you draw a line, you may miss some points, especially the last point. If I draw a line, that line could be something like this, but I may miss that point. So I had better take another trend for that. It may be something like that. It's a smooth curve. So let me write smooth curve passing through all uncertainty zones. Estimately, it can pass through all points or the uncertainty zones. Okay. Part C. The student hypothesizes that V is proportional to N. V is proportional to N. I may be suspicious about if the velocity is proportional to N or no. Anyway, so proportionality is V is proportional to N. Means that V versus N is gonna be a line passing through the origin, or V2 over V1 is gonna be N2 over N1. If I take two corresponding values, the ratios must be the same. These are different aspects of proportionality. I should prove one of them. I think this one is good. From the graph opposite, let's read it. Use the data points. Yeah, use the data points for n equals 2 and n equals 4, 2 and 4 here and here. From the graph opposite to show that the hypothesis is incorrect. Good. So let's check that. It's very easy. I check this point and this point. Let's do something like that. I told you V2 over V1 is going to be N2 over N1. You know that, in other words, I can write V2 over over N2 is V1 over N1. N2 is 4. N1 is 2. I have two values for N and the corresponding values. So I take V over N. If the V over N at this point is the same value, has the same value at this point, so it will be a linear and proportional relation. If it is not, I cannot say that it is proportional. Anyway, it may be linear, but not proportional. Proportionality, you know, has an extra condition rather than linear relation. Okay, it apparently is not a line. Even if it is a line, this line will not pass through the origin. I see that. But I'm gonna show that in different way. I told you, not through the visualized method, but by checking that in calculation. So let's take v over n for this point. Velocity or speed over n is easily 2, and v is gonna be this value. It's about maybe 24, something like that. And yeah, 0.24. So if I divide 0.24 by n, which is 2, it's gonna be 0.12. I will check v over n again, 0.085. And as you see, n is 4 here, and the velocity is 0.34. Yeah, and so it's 0.085. Yeah, they are not equal. So v over n cannot take the same value for the two separate points. So it is not proportional. Maybe linear, but not proportional. Anyway, when they say proportional, you know that you have to prove that v versus n is a line, and this line will pass through the origin, or v over n takes the same value for all points, for all data points. Okay, so we proved that it is not proportional. D. Another student hypothesized that v might be proportional to square root of n. Okay, v might be proportional to square root of n. To verify this hypothesis, he plotted a graph of v squared against n. Okay, we raised both sides to the power of 2. So v squared must be also proportional to n. Here I have v squared and here I have n. Explain how the graph verifies the hypothesis that v is proportional to square root of n. Okay, if v is proportional to a square root of n, v squared must be proportional to n. So v squared against n must be a line. It is a line, and it goes through the origin. So it has two conditions. V squared against n is a straight line that goes through the origin. Problem 3. The graph below shows how the ring diameter d varies with the ring number n. The innermost ring corresponds to n equals 1. Okay, here I have a pattern of some concentric rings, and the number of ring is indicated here. And on vertical axis I have d in centimeter, the diameter of the ring. The corresponding diameter is labeled in the photograph. Okay, error bars for the diameter d are shown. I have some error bars on vertical to indicate the uncertainty of d, but n cannot have any uncertainty as it's an integer and we count the rings. Okay, part A. State one piece of evidence that shows that d is not proportional to n. You know that if y is proportional to x, they must have a linear graph and the line is going through the origin. As you see, I cannot draw a line here. The line of best fit is not a line, it's a curve. Even if I draw a line, the line will not pass through the origin. So, because of two different reasons, it is not proportional. First, the line of best fit is not straight. It's a curve. Line of best fit does not go through the origin. The second one. So, these are the two different reasons for me indicating that d is not proportional to n. Part B. On the graph, draw the line of best fit for the data points. Okay, line of best fit is something like that. It could be a smooth curve that does not go outside the error bars. Try your best to draw it, going through all the error bars or uncertainty zones. I should emphasize that ignore extrapolations below n equals 1. If you extend it to check if it goes through the origin or no, it's an extension. But if you draw the best fit line, avoid that. just start from the beginning, the given value, and end it here. Do not go beyond the given data. Okay, part C. Theory suggests that d squared is equal to kn. Seems that d is proportional to n. Sorry, d squared is proportional to n. K is a kind of constant. A graph of d squared against n is shown below. Okay, error bars are shown for the first and the last data points. Here for the first and here for the last data point, I have some error bars, vertical error bars, but I don't have any for the other data points given. Okay, let's go ahead. Part I, using the first graph, this is the first graph, calculate the percentage uncertainty in d squared of the ring n equals 7. We are going to find percentage uncertainty of d squared. Look at it, it's very important. So let's take a new quantity like q. Q is d squared, okay? Percentage uncertainty for q, delta q over q, is exactly percentage uncertainty for d squared. It's gonna be 2 delta d over d, based on the theory I have already mentioned in previous videos. So you know that, 2 delta d over d. I need two quantities. First is d. Let me show the d by blue color. Yeah, d is here for n equals 7. D is here. Okay, and delta d. Delta d here is the uncertainty, and it's obtained from the error bars. So if I have delta d here, and if I have the d here, I can find the uncertainty for q, percentage uncertainty for q, or percentage uncertainty for d squared. This is something I will do. So let's go for the uncertainty. Here it's n equals 7, and then if you measure from here to here, it will be 2 delta d. So based on that, delta d is gonna be 0.08, because 2 delta t is almost 0.16 here, and so delta d is 0.08 centimeter. This is one part of my structure, the fraction, and then fractional uncertainty will have also d here, so I need the value of d also. So I try my best to find the value of d. D is almost here, a little bit greater than 1.2, maybe 1.26, yeah. So the d is gonna be 1.26, I put it here. Delta d is something I have already found, 0.08, I told you. So the fractional uncertainty is 0.13. If I multiply it by 100, I can easily find the percentage uncertainty, you know. So the percentage uncertainty for d squared is 13%. Okay, let's continue. Double I. Based on the second graph, this is the second graph here, state one piece of evidence that supports the relationship d squared is equal to kn. You know that when I write d squared is equal to kn, and if k is a kind of constant, it seems that I have supposed that d squared is proportional to n. If this is proportional, it must be a line, and also that line will pass through the origin. Seems that it's true here. So I can write an answer like this. It is possible to draw a straight line, as you see that a straight line, that passes through the origin and lies within the error bars. Triple I. Use the second graph to determine the value of the constant k as well as its uncertainty. K must be something like this: a value plus or minus uncertainty. Let's first find the value and then the uncertainty. When I write d squared is equal to kn, means that d squared versus n is a line and k is the slope. For finding the slope, I always use a right triangle like this. I put the hypotenuse exactly over the best fit line, and then I write vertical over horizontal to find the slope. This gives me the value. Then we will look for uncertainty. The vertical is the height of this triangle from here to here is 2.5. It's very easy to find. And horizontal from 1 to 12. So it's 11. That's all. I divide them, height over base, 2.5 over 11, and I find the value to be 0.22. But for the uncertainty, the strategy is different, you know. Uncertainty for K is gonna be half of the range. K max minus K mean over 2. K max is the maximum slope. I should connect for the first point, the bottom, to the last point, the top, and find the K max. Then I should do something similar for K mean. For the first one, the top, the last one, the bottom. So I will connect these two, and then I will find K mean. Then I put them in this formula to find the uncertainty. Okay, let's start one by one. First, look at this point, the first bottom and the last top. Then I establish a triangle again. The vertical is 2.8, the horizontal is 11. If I divide them, it gives me K max to be 0.25. Then I establish another triangle for finding the minimum slope. For the first point, the top, for the last point, the bottom, and then I establish another right triangle. The vertical will be 2.1, the horizontal is 11, and then I divide them again. This is 0.19. That's all. Half of the range will give me the uncertainty. Maximum minus minimum over 2, 0.03. So the value of K will be 0.22, and the uncertainty, which is denoted by plus or minus, 0.03. Okay, the last part of this problem is state the unit for the constant K. The unit is very easy anyway. N does not have any unit, so the unit just the unit of d squared. As the d squared has the unit of centimeters squared, so I think the unit of K also will be centimeters squared, because I find the value of K by vertical over horizontal. As the horizontal does not have any unit, the vertical will have the same unit as K. So centimeters squared. I hope you enjoyed. If you enjoyed, give me a like and don't forget to subscribe if you are new to this channel. Don't forget to push the bell button to see more videos. See you in the next video.